Well, welcome to evanecent, my YouTube channel. I've made about 60 odd videos about projects on engineers' lathes, but one of the most popular ones is a video called Understanding Gear Trains, and it's had 21,000 visits in the last 4 years. I decided it was time to have an upgrade with perhaps some better graphics. So I've made a whole lot of slides with Photoshop, and we'll go through how to calculate the gear ratio, and first of all starting off with a bit of anatomy about how the lathe works and why the parts are named the way they are. That'll help a bit too. Okay, let's go. This is my 1955 Boxford Model A Imperial lathe that we'll be tearing apart to have a look at the gear train. When we open the door at this end of the lathe, we'll find the gear train inside. When I said we were going to be tearing it apart, I wasn't joking. This is the head after I'd taken it all apart, and the main thing I want to show you is a spindle. The spindle is a shaft that runs right through the center of the head, and on the right hand end we have a thread with the chuck mounted on it, and at the left hand end there is a gear that's machined into the shaft of the spindle, and that's called the spindle gear, and we'll talk about that later. This illustration also shows the pulleys where the motor is actually driving the spindle, so it's actually the driving mechanism. This is the actual spindle shaft that I took out of the head, and you can see now that it's got the spindle gear machined on the left hand end and a thread on the right hand end, and it's held in place by tapered roller bearings. This is a little sketch that I made for our Boxford users group to show how the tapered roller bearings are opposing each other and preventing the shaft from having any lateral movement at all, and yet being able to rotate well. And it's adjusted with a ring threaded nut on the end which pushes the two roller bearings together. This is the gear train on my lathe after it had been cleaned up and some paint applied. But this is what it looked like before it was cleaned up. But these are the best photographs I actually have of the gear train in various stages. After removing most of the gears, you can see the Y-shaped banjo, and this provides a lot of different ways of mounting the gears. There's a bolt you can see there that is used for mounting the gears in the slots, and it gives a lot of flexibility. In the bottom of this photograph you can see a shaft and a large clamp around it with a square-headed bolt which is used to clamp it into place, but loosening this bolt allows you to shift the gears around so that they mesh properly. Now we can mount some gears on there and see how it goes. This setup is actually for converting from imperial to metric, with a pair of compound gears right in the middle, the two big gears, and we'll come back to that point later. Now we can see it in action, and the set of 4 gears at the top left hand corner are simply for reversing it, and later on we'll show how they can be removed from your calculations. Then we've got the double compound gear, and the second to last gear is simply an idler gear to make it rotate in the correct direction. So we can see that the stud gear at the top left hand corner is rotating in the same direction as the lead screw gear at the bottom right. And now after removing that idler gear, we can see the rotation is in the opposite direction, so the lead screw gear is now rotating anti-clockwise and the stud gear at the top left is rotating clockwise. I must give a plug for this excellent software by Able Vince, which produces these beautiful graphics and is basically free of charge. It can be found at geargenerator.com. Now let's get down to the real nitty-gritty of calculating gear ratios, and we'll start with a simple 2-gear system. The most important thing here is to make a clear distinction between the driver gear and driven gear. The driver gear here is driven by the motor, and it's meshing with a second gear, which could, for example, be connected to the lead screw, driving the carriage along the lathe. The gear ratio is calculated from the number of teeth on each gear, so you write in here 30 teeth on the driver gear and 56 on the driven gear. Now we can calculate the actual gear ratio, driver over driven. That's the key thing to remember. The driver always goes on the top line and driven always goes on the bottom line. And if you have a collection with a lot of gears, all the driver gears go on the top line and all the driven gears go on the bottom line. In this case, the driver gear has 30 teeth on the top line and the driven has 56 teeth, and this gives a ratio that's roughly 0.5. So you'd expect the driven gear to be turning about half the speed of the driver gear. So let's have a look. Yes, I'd say that's about right. Notice, however, that the larger driven gear is rotating in the opposite direction to the driver gear, and that's typical. The place where the two gears touch is called the meshing point, where one gear meshes with the other, Look at how many teeth are passing through that meshing point with each rotation. The smaller gear rotates once and passes through 30 teeth, but the larger gear has almost 60 teeth, so it will only turn half the speed, and the small gear will have to turn almost 2 full turns to pass 56 teeth through to the second gear. Now we're going to make things a bit more complicated by adding a compound gear between these two gears. This example of a compound gear is used for converting from imperial to metric, and the two gears are actually riveted together. You can see, if you look closely, a round rivet. So this compound gear is actually two gears connected together with this rivet, or some other way of making them rotate together, and they are known as a compound gear or a transposing gear for changing between imperial and metric. And this shows how it works. With the smaller gear at the top left hand corner is driven by a motor and is driving the larger of the compound pair, and the smaller of the compound pair is driving the lead screw gear at the bottom right. So now we have to make the important decision about which ones are drivers and which other gears are driven. So the motor drives the top left-hand small gear, so that's the driver, and it's driving the largest gear, which is driven, and then the smaller compound gear is another driver, which then drives the very last gear on the bottom right corner, and that's called a driven gear. You'll notice that they always alternate driver driven, driver driven. Now let's write in the number of teeth on each of these gears: 30, 127, 100 and 56. Now to calculate gear ratios, we'll look at one pair at a time. So the first pair are the 30 tooth driver and the 127 tooth driven. On the right hand side we see the gear ratio calculated with the driver of 30 over the driven of 127 gives you the gear ratio. So that was for the first pair of driver and driven. Now we do the second pair of driver and driven gears. 100 driver over 56 driven gives the ratio for that pair. Now we're ready to combine the two pairs, and they're just multiplied together. So the overall gear ratio for the whole gear train is the top pair 30 over 127 multiplied by the bottom pair 100 over 56. When we put those numbers in a calculator, we find the gear ratio is 0.42. Now let's give the gears names. The top gear is the stud gear. Next one down is the first compound gear, or comp 1, and the second gear is the second of the compound pair, called comp 2, and finally we come to the lead screw gear, which I call LSG. Now we can use our gear ratio equation, but instead of using the number of teeth on each gear, we just write down its name, and hey presto, we have algebra. So the gear ratio is stud gear over comp 1 multiplied by comp 2 over LSG. That's our equation. With the previous numbers that we entered, we got a gear ratio of 0.4218. That means that the lead screw gear at the bottom right should be turning at about 0.4 times the speed of the stud gear at the top left. And that looks about right. Now, instead of using a pair of compound gears in the middle, we're going to replace it with a simpler looking single gear. And that's called an idler gear, and we'll soon find out why. Well, once again, we have to decide which is a driver gear and which is a driven. Situation is the same again. We've got the motor driving the driver gear at the top left, and it's driving a bigger gear, which is a driven gear. And then we assign the number of teeth to each gear, and the driver has 30 teeth and the driven has 80 teeth, and that gives a gear ratio of 30 over 80. Now when we come to the second pair, it's a little bit strange, because what was previously a driven gear is now a driver gear. It's a bit like having a pair of compound gears where both gears have the same number of teeth. It would behave like this. So the second gear ratio we calculate uses the 80 tooth gear as a driver and the 56 tooth gear as driven, giving a gear ratio of 80/56, 80 over 56. Now when we put these two ratios together, you can probably guess what's going to happen. We multiply the 30 over 80 ratio for the first pair by the second ratio of 80 over 56 for the second pair. Since the number of teeth on the idler wheel cancel out, it doesn't really matter how many teeth are on it. Since the number of teeth on the idler wheel cancel out, it really doesn't matter how many teeth it has, and it is common just to write any. So I say here, lazy bones idler never does any work, but changes direction. So that's the only useful thing about it really, is that it fills a space, which is actually the most common reason to use it, and also to change direction so that the lead screw gear rotates in the correct direction. And to rub in this really important point, another illustration showing the idler wheel in pink, but we completely ignore it when we calculate the overall gear ratio. It's just 30/56, and just ignore the idler wheel. And this arrangement with the idler wheel is really just the same as this one without an idler wheel, giving the same gear ratio, 30/56. Now that we know all about idler wheels, we can go back and look at these tumbler gears that are used for changing direction of rotation, because they involve idler wheels that do nothing but change rotation. So look carefully how the power is transferred through the first gear to the second, third, and then into the stud gear, and the effect that it has on direction of rotation. So in the first position, the lead screw gear is turning clockwise, but as the tumbler gears are moved slightly, the lead screw gear is now working in the opposite direction, anti-clockwise. So let's switch the tumbler gears again, and now we've got the lead screw working clockwise, and we'll switch again and make it go anti-clockwise. Looking again closely at the positions of the gears when it's in the anti-clockwise rotation, and you see that one of the gears is just sitting there doing nothing. It's just going round and round. It's still meshing with the other idler gear. The next important point is to look at the gear ratio of this tumbler system. The driver gear, the actual spindle gear, it has 30 teeth on it, but also the driven gear underneath the stud gear has 30 teeth as well, and this gives a gear ratio of 1. This means that the stud gear turns at exactly the same speed as the spindle gear, and that's why in subsequent calculations we can completely ignore everything above the stud gear, because it's a 1-to-1 ratio. We don't have to include it in our calculations. Now that was in reverse direction. Now look again at the forward direction and see how the power is transmitted through the gears this time. In this case, both of the tumbler gears are acting as idlers with power running through them, and each time it goes through another gear, the direction of rotation reverses. So now we've altered the overall number of gears from an odd number to an even number. And we can see the power transmission sequences from 1 to 2 to 3 to 4 to 5 to 6 in this gear train. This photo illustrates the point that the reversing gear has 3 positions, and in this photo it's in the neutral position where it doesn't drive the lead screw gear at all, but you can lift it up to go in one direction and push it down to go in the other direction. This photo shows the actual stud or shaft that the stud gear is mounted on. And of course there are 2 gears mounted on the shaft with the keyway, and the key makes sure that both gears rotate together. In this photo you can see that the outer stud gear is held on with a nut to stop it from falling off, and there are actually 2 gears on this shaft as we saw on this keyway, and that the tumbler gears drive the smaller gear, which should never be changed. It's supposed to have the same number of teeth as the spindle gear. And I have seen cases where somebody has bought a lathe and found that somebody had changed this gear to a different size, and that messed up all their gear train calculations. And it's quite tricky to find that problem. What's usually changed is not that inner one which says do not change, but the outer one that's marked stud gear. This stud gear is the one that's most commonly changed when we want to alter the gear ratio of the gear train. But you can alter all the other gears down from that, but never alter the one that's at the base of the stud. In this view we can see the plain stud gear, the blue stud gear, mounted on the stud shaft, and the special gear behind it can't be seen, so it's not very obvious. This is an edge view of the same gear train, and we can see that blue stud gear is driving a double compound or compound gear made up of 2 gears, and the second of the compound gears is driving the lead screw gear. Notice how the lead screw gear has a spacer or something behind it to make it line up with that second gear. Now back on the straight on view of the same gear train, and you can see in this case the 40-tooth stud gear is driving the 127-tooth compound gear, which is connected physically to a 100-tooth gear, which then drives the lead screw gear. Now that we've given names to these gears, we can write down the equation for the overall gear ratio, starting with the stud gear. And the gear ratio is stud gear, over compound 1 multiplied by compound 2 over lead screw gear. And that gives us the overall gear ratio in an algebraic form. Now we come to a new useful tip which I haven't mentioned before, and that is that the gear ratios are calculated around the point that gears are meshing with each other. So I've illustrated on this diagram how the stud gear is meshing with compound gear 1, and that mesh point decides where we're going to calculate the ratio itself. So the first gear ratio is stud over comp 1. A second point that gears mesh with each other is then marked a little further down, where comp 2 meshes with LSG. So that forms the second ratio. So then we calculate the overall gear ratio with the same equation, stud over comp 1 times comp 2 over LSG. But looking for those meshing points is a useful way of figuring out where you have to calculate your ratios, where the gears pair up. Although this looks a bit like the stud gear shaft, this is actually on the lead screw end, and it has a short keyway there that allows you to place a gear which is going to drive the lead screw. So if you have a lathe without a gearbox, this is actually the end of the lead screw shaft, but in this case there is a gearbox and this is the input to the gearbox. But to be consistent, I still call this the lead screw gear, or LSG for short. Notice too that there's a spacer there which makes that keyway look short. That spacer is to allow the next gear to be placed over it to mesh with the outer of the compound pair. If you want to mesh with the inner of the compound pair, then you have to remove the spacer. And often instead of a spacer, they'll use a small gear wheel. This can be sometimes confusing on gear diagrams when there's a gear wheel in there that doesn't actually connect to anything. This is actually the Norton gearbox on my Boxford lathe, and we're not going to be talking about gearboxes today, but I just thought I'd give you a brief look. This is a 40-speed gearbox which has a series of gears of different sizes which line up like a Christmas tree, designed by an engineer by the name of Norton in the 1880s, but there are a lot of variations in the actual gear ratios used. This is a professional engineer's drawing of the gearbox, and you can see those arms that are used to select which of the gears you're going to mesh with. I just mentioned the gearbox because if you do have a gearbox, you have to take that into account when you're working out what thread will be produced by a particular gear ratio, or vice versa. With a gearbox, it's less likely that you'll need to change the gear train, and in fact, to use the tables that they give you, you have to use a specific gear train for it to work, and I refer to that as the standard gear train. As you can imagine, there are a lot of different ways you can arrange the gears on the gear train and produce a lot of different gear ratios. And in fact, the more gears you have, the more gear ratios you could theoretically produce. And I had one user who contacted me that had 36 gears to choose from, and he wanted to use 2 pairs of compound gears on the gear train because that's a pretty standard setup on Chinese lathes. So how many combinations of gears can you get with this setup? Well, this depends on how many gears there are in the chain, and with 2 compound gears you have a total of 6 gears in series. And this is what it looks like. There may also be an idler gear thrown in there somewhere. So this is how I number the 6 gears. The stud gear, and 2 and 3 are the first pair of compound gears. 4 and 5 is the second pair of compound gears, and gear 6 is the lead screw gear. Now we're going to calculate the number of combinations there are with this setup. So we're making a gear train with 6 gears, and the first gear we choose, you have 36 choices from your stack of gears to put in. But when you come to the second gear, you've only got 35 left. So the combination of doing the same thing through 6 gears is you have 36 the first time, 35 the second time, 34 the third time, and so on. Multiply by 33, multiply by 32, multiply by 31. So those are your 6 different gear choices. Multiply all those together and you get 1.4 billion. And so how can a person decide which one of those 1.4 billion setups they're going to use? Well, the usual way is to rely on the manufacturer to give you some charts like this to just look up what gear setups you're going to use. Actually, this is for my lathe with a gearbox, so it's telling you what gear lever positions to use, but other ones will show you which gears to use in a gear train. For example, this label on my lathe shows how to set up a gear train to cut metric threads on an imperial lathe using those compound gears we were just looking at, and what gear you need to put on the stud gear position to get the right speed. So each lathe will have a different label depending on the manufacturer. Now if your lathe is missing these labels, or you have gears missing, or you have more gears than the label normally covers, or you have a very odd thread that you're trying to make that's not on the standard tables, there's a computer program which I've written that solves this problem, and it's free and available online. So it's simply at RideTheGearTrain.com. When you run this program, you see a series of buttons come up in the main menu, and although this might look complicated at first glance, it actually makes it easier to use. So when you want to specify whether your lathe is metric or imperial or various other types, you click the first button, and then after that you design your gear train. That is deciding whether it has 0, 1 or 2 compound gears that we've been talking about. In step 2b, you just enter the list of gears that you have. In step 3, you specify whether you want a metric or imperial thread that you want to cut, or various things like feed rates. And in step 4, you specify how much error you're willing to accept. You might just say 0%, in which case you get fewer results. But more commonly, we'll put in, say, 1% error as the maximum we can accept. And then in step 5, we specify how many threads per inch or millimeters pitch that we want. And we can enter that as just a single number in step 5a. There are more complicated alternatives. In step 5b, you can put in a range of values, or in step 5c, you can look up standard tables to find out the pitch or threads per inch. So it's really quite simple to use. Once you've entered all that data, you press run and it shows you all the different gear chains you can set up to produce that thread. So this is part of the table of results that I got, but I had a large number of gears and it produced 500 possible solutions to the problem. And these are the ones listed at the top of the list that have 0%, so they're sorted into order by percentage error. So this is showing us a symbol on the left-hand side that indicates whether the gears are likely to fit on the gear train and the level of accuracy of the results. And so if it's got lots of hashes and stars, then that's a good choice. And the next column shows the threads per inch we're going to get. The next one is the percentage error for that particular gear train. 1 over the gear train ratio, which can be multiplied by the gearbox setting to calculate the actual thread. The next column is the stud gear, what gear you're going to use there, and compound 1, compound 2, and the lead screw gear. And finally the gearbox setting if you have a gearbox. And finally, once you've chosen one of these threads, you click on the draw button on the right hand column and you actually get a picture of what the gear train will look like as a scale drawing. Just glancing at this drawing helps you decide whether the gears are likely to fit together. And in fact, the computer program tries to do the same thing and will give you a message to say that the gears don't look as though they'll be able to be connected together without banging into each other. There's also a list of other applications in the suite that are useful, especially for hobby engineers. The first one's about electronic lead screws, which could be used in place of the gear train. The next is about the metric imperial conversions, so cutting metric threads on an imperial lathe or imperial threads on a metric lathe. And that's such a big topic, I think it may be worthwhile going over it in a separate video. The third button on this list tells you the specifications of any particular standard thread, and it also tells you what size drill to use when you're using a tap to cut a thread. The fourth button there tells you how to set up taper turning, especially with the tailstock offset method. And the next one is cutting speeds, calculators, and tables. And finally we come to hardness of materials, so tables of all the different kinds of metals and their hardness, and also the cutting speeds that are required for different hardness of metals. And finally we come to the one which is most fun to play with, is the polygon cutter. So let's see how that works. Well, you've made it to the end of this rather long video, and hope you liked it, and let us know if you do.